Welcome back to study room. So today we'll be studying about characteristics of sound. So let's get started. So as I told you, sound travels in medium. Sound needs a medium to travel, correct? So if sound needs a medium to travel, so it can travel through, we know three mediums, right? Solid, liquid or gas, okay? So sound travels through solid, liquid and gas, all of them, okay? Most of you might think that how can the sound travel through solid, right? But you're wrong. Sound travels the fastest through solid, then liquid, then gas. So basically, sound needs a medium for propagation and it travels fastest through solid, okay? Sound waves are longitudinal waves, okay? A wave vibrating in the direction parallel to the direction of propagation is called longitudinal wave. So longitudinal wave is parallel to the direction of the propagation. And what is transverse wave? As the name suggests, transverse means perpendicular, okay? Transverse means perpendicular. So wave vibrating at right angles to the direction of its propagation is called transverse waves. So you can see the nature of both the waves in the given slide, okay? Some more examples of longitudinal and transverse waves. So you can see this is a longitudinal wave, okay? Like the spring. And this is a transverse wave, water droplets, okay? Characteristics of sound waves. So sound waves can be characterized by three terms, like, right? So it can be characterized by frequency, amplitude and speed. So we'll study in detail about these three. Okay, so sound wave can be characterized by the frequency, the amplitude and the speed. Okay, so let's look at this diagram. Okay, so we can see density variations. So we just studied about this in the previous slides. Compression and rarefactions. Okay, what was compression? High pressure region, right? And what was rarefaction? It was a lower pressure region. So sound is nothing but a combination of compressions and rarefaction. So you can see high pressure, low pressure, high pressure, low pressure, high pressure, low pressure, right? So these are density variations. Somewhere it is high pressure region, somewhere it is low pressure region. Sound is a combination of these. So you can see that density of pressure varies this way, okay? With the distance, okay? Density or pressure. So the uppermost part is called crest and the uppermost point is your crest and the lowermost point is called trough, okay? Sound propagates as density or pressure variations. Compressions are regions where particles are crowded together and represented by the upper portion of the curve. So we talked about this, right? This is a high pressure region. Then rarefactions are the regions of low pressure where particles are spread apart and are represented by the valley, that is the lower portion of the curve. This is your lower pressure region, right? Rarefaction is your lower pressure region. Crest and trough. A peak of the wave is called the crest and a valley is called the trough, right? So these all are your peaks, right? Uppermost, topmost. This is your crest and these are your valleys. And what are they called? Trough, okay? So this is how the wave is propagating. Wavelength. What is wavelength? We denote wavelength with lambda, okay? So the distance between two consecutive compressions or two consecutive rarefactions is called the wavelength. So just like in this, we can say two consecutive compressions. The distance between two consecutive compressions, right, from here to here, or two consecutive rarefactions are called wavelength. This is also lambda, this is also lambda, okay? Okay, so the wavelength is usually represented by lambda, okay? Lambda. So, and since wavelength is a unit of distance, okay, so it is represented in meters. So what is frequency? The change in density from the maximum value to the minimum value, then again to the maximum value, makes one complete oscillation. Okay, so what do we mean by this? For example, let's see in this diagram. So you started from here and you came here, right? 1. And right, from here maximum to minimum, then minimum to maximum. So one complete oscillation has completed from here to here. Okay. So the number of such oscillations per unit time is the frequency of the sound wave. The number of times this oscillation is repeated is known as its frequency. It is usually represented by nu. Okay, nu. We represent frequency by nu. And it is actually the inverse of time period. So frequency is equals to T inverse is equals to 1 upon time period. So if you know the time, you can tell the frequency. Okay. Okay, so what is the unit of frequency? Frequency, as it is 1 by T, it's second minus 1, right? And its SI unit is hertz. For frequency, the SI unit is hertz. So you can see this is a lower frequency because low, the number of cycles completed in the same time interval is lesser in this particular case, in case 1. And in case 2, you can see that in the same time period, a large number of oscillations are completed. Okay, so complete cycle. We see frequency via the complete cycle, and we see that here more number of cycles are completed, so it has a higher frequency. Okay. What is time period? The time taken for one complete oscillation is called a time period, right? We started from here and we came here. So this is your one complete oscillation. Then again this 2 complete oscillations, okay? And this will continue. For example, if I ask for this wave, so how many, what is the frequency? Since this whole pattern is repeated 3 times, it will be frequency is equals to 3. Okay, so did you get the time period? So time taken is one complete oscillation. The time taken for one complete oscillation is called time period. It is denoted by T. And what is the SI unit of time? SI unit is seconds. Okay. Relation between frequency and time period. Okay. Frequency is measured in hertz, which is equal to 1 event per second. Frequency is equal to second power minus 1. The period is the duration of the time of one cycle in a repeating event. So the period is the reciprocal of the frequency. Okay. So frequency, we denoted, it's not V, it's frequency. It's like a little curve. Okay. Frequency is equals to 1 upon time period. Okay. So let's hear these 2 sounds and you tell me what is the difference between these 2 sounds. Okay. So the difference between these 2 sounds is that, this sound has a higher pitch. Okay. This sound has a higher pitch and this has a lower pitch. So both the sounds have different pitches. Okay. Pitch. The faster the vibration of the source, the higher is the frequency and higher is the pitch. Okay. So pitch deals with your shrillness of voice. Okay. Like, I can just, help you figuring out. For example, I say, hello. And I say, hello. So, hello has a higher pitch. Okay. So, higher is the frequency, higher is the pitch. Thus, a high-pitched sound corresponds to the number of compressions and rarefactions, okay, passing a fixed per unit time. For example, low frequency, low pitch, slow sound, okay. So, for example, this is the graph for that. Low frequency, low pitch and low sound. High frequency, high pitch and high sound. This is this type of graph. That means more number of complete cycles took place in this case, right? Okay. So, low pitch and high pitch. So, these are the graphs for both the pitches. So, a low pitch sound will have a lesser frequency and a high pitch sound will have a higher frequency. Okay. So, characteristics of sound. What is amplitude? The magnitude of maximum disturbance in the medium on either side of the mean value is called the amplitude of the wave. Okay. So what is it? It is the magnitude of, it is the amount of maximum disturbance on the either side of mean value. Okay, so it is usually represented by A. So this is a low amplitude, it's a quiet sound like shh, hello, hello. This is a low amplitude sound. Hello. This is a high amplitude sound, right? So a low amplitude sound is very quiet, very low. And a high amplitude sound is a loud sound, okay? Loudness. So the amplitude of the sound wave depends upon the force with which an object is made to vibrate. Loudness, louder sound can travel a larger distance as it is associated with high energy. Loudness is determined by the amplitude of the sound, okay? And pitch was determined by the frequency, okay? So loudness determined by amplitude, and pitch was determined by frequency, okay? Soft sound and loud sound. So as you can see, this is your soft sound, you know, your wave disturbance is lower in soft sound. You know, the height of the graph is low. And for loud sound, you have a greater amplitude, right? Amplitude is lesser in soft sound, okay? You can just see. And amplitude is greater in loud sound. Tone and note. A sound of single frequency is called a tone, okay? The sound which is produced due to a mixture of several frequencies is called a note, okay? So if we are talking about a single frequency, that is, we are talking about just one frequency, then it is your tone. And when we are talking about multiple frequencies, that is like your mixture of frequencies, right? We are talking about a note, okay? So question 1, which wave property determines loudness and pitch? You know, loudness is determined by what? Correct, you are correct. We just discussed it, amplitude. And pitch is determined by frequency. So loudness is determined by the amplitude of the sound. Higher the amplitude, louder is the sound. And pitch is determined by the frequency of the sound. Higher the frequency, more is the pitch, okay? Guess which sound has a higher pitch, a guitar or car horn? Now you guess which has a higher pitch. Of course, a guitar has a higher pitch, right? Because, you know, if we talk about a guitar, we have a lot of strings. So particles, vibration, a large number of vibration occurs, right? A lot of vibration occurs. So pitch of sound is determined by the frequency of vibration of waves, and if the frequency is higher, we say that the sound is shrill and has a higher pitch. The guitar has a higher pitch because the particles vibration frequency is higher in guitar as compared to a car horn, right? More vibration because more strings, right? In guitar. So guitar will have a higher pitch. Now let's study about speed of sound. The speed of sound is defined as the distance which a point on a wave such as compression or a rarefaction travels per unit time. So compression was your high pressure region and rarefaction was your low pressure region, right? So your speed, we know speed is equals to distance upon time, right? What is your distance? Distance is your lambda. What is your time? Time is your 1 upon nu, right? So what is your speed? Speed is given by, okay, C, we say C for the speed of light in air. But right now let's write it velocity V, okay. V is given by lambda upon 1 by nu because lambda upon time and time is your 1 by nu, right? It is the reciprocal. So V is equals to nu lambda, okay. We can say this, that speed of sound is given by nu, your frequency and your wavelength. So you gave the speed of sound in terms of your frequency and your wavelength, okay. 1 by T is equals to nu. So let's do this example. A sound wave has a frequency of 2 kilohertz. Your frequency is 2 into 10 to the power 3 hertz, okay? And has a wavelength of 35 centimeters. Lambda is your 35 centimeter. How long will it take to travel 1.5 kilometers? They are asking you about the time, that how long will it take to travel 1.5 kilometers. Okay, so let's do this together. We have just studied that V is equals to nu lambda, right? So it is equals to, what is your nu? 2000 hertz, right? 2 into 10 to the power 3 hertz into what is your lambda? 0.35 meters, because 35 centimeters will convert it into meters, right? So it comes out to be 700 meter per second. Okay, so this is your velocity. So now the time taken by the wave to travel a distance. So we have to calculate the time. We know time is distance upon velocity, right? What is your distance? Distance is your 1.5 kilometers. That is 1.5 into 1000 meters. Upon what is your velocity? 700. Okay. So 700 meter per second. So this comes out to be 2.1 seconds. Okay. So we get that the sound will take 2.1 seconds to travel a distance of 1.5 kilometers. Let's do one more question. What are wavelength, frequency, time period and amplitude of a sound wave? So we have discussed it. So let's do a quick recap. So wavelength is the distance between two consecutive compressions or two consecutive rarefactions. Okay. So what is the SI unit of wavelength? Since it is a type of distance, the SI unit is meters. Okay. So what is frequency? It is the number of complete cycles, right? Number of complete oscillations per second. It is measured in hertz. What is amplitude? It is the maximum height reached by the crest or the trough of a sound wave. Okay. So how are wavelength and frequency of a sound wave related to its speed? We know wavelength is lambda and your frequency is nu. And we know that velocity is equals to nu into lambda. So this is how your wavelength and frequency are related to speed. The speed is the product of your wavelength and your frequency. Okay. One more question. Calculate the wavelength of a sound wave whose frequency is 220 hertz and speed is 440 meters per second in a given medium. Okay. So let's calculate. So your frequency is 220 hertz. Okay. And what is your speed? Your V is 440 meter per second. We need to calculate lambda. Again, the same type of question, right? We know the formula V is equals to nu lambda. We'll just plug in the value. So 440 is equals to 220 into lambda. Then what is your lambda? Lambda is nothing but 440 by 220, right? So lambda is 2 meters. Okay. Let's do one more question. A person is listening to a tone of 500 hertz sitting at a distance of 450 meters from the source of the sound. What is the time interval between successive compressions from the source? Okay, so let's do this quickly. So you are seeing that, distance is also given in this question, right? But you have nothing to do with the distance, okay? So what is the time interval between? We know that time interval is nothing but reciprocal of frequency, and we know the frequency, that is your 500 volts. So in this question, we have nothing to do with the distance, okay? So what will be the time interval? 1 upon 500, that is your, how much? 0.2 upon 100, that is your 0.002 seconds. Okay, so this is the time interval between successive compressions. Okay, so we can also say that it is 2 milliseconds. Okay, so intensity of sound. So what do you mean by intensity? Intensity is the amount of sound energy passing each second through unit area. Okay, so let's distinguish between loudness and intensity of sound. Okay, so loudness is the measure of the response of ear to the sound. Okay, and what is intensity? It is the sound power per unit area. So loudness and intensity are not the same. Most people get confused in this. Okay, so loudness is measured in decibels. Okay, it is measured in decibels, and intensity is measured in watt per meter square. Okay, so loudness is dependent on sensitivity of human ear, while your intensity is independent of sensitivity of human ear. Okay, loudness is a subjective quantity, It depends on the amplitude, right? And intensity is an objective quantity. Okay, so sound propagates through a medium at a finite speed. The speed of sound depends on properties of the medium. So, speed of sound depends on many factors, right? It depends on temperature, density, right? So, it depends on many factors. Okay, nature, environment, right? So, the speed of sound in air is 331 meter per second at 0 degrees Celsius. Okay, this is your freezing point, right? And 344 meter per second at 22 degrees Celsius. So in which of the three media, air, water or iron, does sound travel the fastest at a particular temperature? So you tell, since we have already studied that, speed travels fastest in solids. Okay, so speed of solids is fastest, then comes the speed of liquids, then comes the speed of air. Okay, speed of particle in air. Okay, so from air, water and iron, since iron is a solid, so sound will travel fastest in iron. Then in water and then in air. Okay, so speed of the sound depends on the elasticity of the medium. As solids have the highest elasticity, it travels fastest in solids. Elasticity is less for liquids and least for gases. Hence, its speed decreases in liquids and it is slowest in gases. Therefore, for a given temperature, sound travels fastest in iron. Okay, sound travels about 1500 meters per second in seawater. Okay, and sound travels much more slowly in the air. So, sonic boom. When a sound producing source moves with a speed higher than that of sound, that is a supersonic speed. Okay, speed is higher. Your speed is higher than the speed of air, right? Speed of sound, right? So it is a supersonic speed. It produces shock waves in air. The air pressure variations associated with this type of shock waves produces a very sharp and loud sound called the sonic boom. So have you seen your TV radars, right? So your dish TVs and all, they work on sonic boom. Okay, so we'll meet in the next video, and thank you for watching and being part of study room. I wish you all the very luck for your studies. Bye bye.